Hi, and welcome to this lecture on the hydrostatic pressure distribution. In this lecture, we're going to derive the hydrostatic pressure distribution for incompressible as well as compressible fluids. The hydrostatic pressure distribution is fundamental for other topics such as dealing with manometers and barometers, as well as hydrostatic pressure forces and buoyant forces. So this is a foundational lecture. So let's go ahead and take a look at the screen. On the screen here you see a picture of someone's basement. Thankfully it's not my basement because they have a real problem here. Here's a basement wall, and you can see this huge crack that's formed more or less horizontally on the basement wall. What's happening here is water's gotten next to the wall on the outside of the basement, and the water is applying some pressure to the wall, causing it to buckle. So let me go ahead and kind of sketch this out for you. Let's say we have the basement wall here. Here's the foundation. This is the basement. Here's the rest of the house sitting up here. Here's the ground on the outside. So what's happening is some water is accumulating next to the wall of the basement. And what that water does is it exerts a hydrostatic pressure on the wall. And we're going to talk about this in this lecture. But there's some pressure being exerted on the wall, and it's creating a pressure force. And that force is causing the wall to buckle. So the wall wants to bend inward like that. And as a result of that, you get this big crack that forms on the interior wall here, or just in the wall in general. That's obviously a problem. It affects the stability of the house, right? It weakens the walls. You can get water coming in through that crack. It's something that has to be fixed. The solution to it is you just try to get the water away from the wall. So you contour the land around your house so that the water washes off to the side. It doesn't collect next to the wall. Sometimes they'll put in a thing called a French drain. It's basically a pipe underneath some gravel, so water comes down, and there's some holes in the top of the pipe. The water will go in the pipe, and then the pipe moves the water away from the side of the house. So all of this comes about, this kind of buckling phenomenon comes about because of the hydrostatic pressure distribution. So that's the topic of today's lecture. So let's take a look at the material here. Let's get started. What we're going to do is we're going to take a look at a little piece of fluid in a big expanse of static fluid. So we're going to be talking about hydrostatics here. One of the things that's important is when the fluid is static, or it has no relative movement, the only forces acting on typical pieces of fluid would be pressure forces. There are no tangential or viscous forces. You only get tangential or viscous forces when you have relative movement between fluid particles. Here the fluid is not moving relative to the other particles. It's static. So the only forces you're going to have are pressure forces, which act normal to the little pieces of fluid here. And you'll see that in a moment. So that's an important thing to keep track of. So what we're going to do is we're going to zoom in on this little piece of fluid. It's very, very small. By the way, in this system, gravity is pointing at some arbitrary direction, and we have some coordinate system. So I'm going to zoom in on that little piece of fluid down here, and I'm going to draw a free body diagram and then do a balance of forces on it. So let's start with the free body diagram. Well, first of all, let's put the geometry on here. So we're going to say it's a small piece of fluid with distance dx in that direction. That's consistent with our coordinate system. dy in this direction. And then dz in and out of the page. Okay, so it's a small cuboidal piece of fluid. We're going to say that at the very center here, the pressure is P. We don't know what that pressure is, but it turns out it won't matter. And then we're going to balance some forces on, we're going to draw some forces on that piece of fluid. So we're going to start with the left-hand side. So I'm going to highlight it in yellow. We're going to start with that surface, and we'll draw the pressure force acting on that surface. Remember, there are no viscous forces here. Okay, so let's start with the pressure force. That will act inward on the surface, as you already know. And that pressure force there will be the pressure times the area of that surface. Now the pressure on that wall is not P. Because it's a little bit off to the side, the pressure could vary a little bit. So here we'll make use of our Taylor series expansion that we've talked about in a previous video. So the pressure over here, let me write it out and then I'll explain it. It'll be P plus dp dx times a minus 1/2 dx. Oops. So that's the pressure on that yellow wall there. The way I've written it here, it's the pressure we start with P plus how the pressure varies in the x direction, that's dp dx. That's the change in pressure over the change in x position. We call that the pressure gradient in the x position, or the pressure gradient in the x direction. A gradient is just how something changes with respect to position. So this is the pressure gradient in the x direction, or just how the pressure varies with x. So this is how the pressure varies with x, and this is the distance we moved from the center of the cube off to the left. It's moved a distance of 1/2 dx in the minus x direction. You can see here is x is to the positive x is to the right, and so we've moved to the left, which makes it a negative. So that's the pressure on that left face. We're just making use of that Taylor series approximation. To get the pressure force, we have to multiply the pressure times the area. So the area there will be dy times dz. Now we can do the same thing on the other face. So let's draw that pressure force. So on the right-hand side, the pressure there will be P plus dp dx times a 1/2 dx, and then the same area dy dz. So again, let's just walk our way through this. So it's the pressure we start with at the center, how the pressure moves in the x direction, dp dx, times how far we've moved to go from the center to the right-hand side. And that's a positive 1/2 dx because we're moving off in the positive x direction. And then we have the same area, dy dz. So those are what we call surface forces acting in the x direction. Surface forces are forces that act on the surface of the cube. We have no viscous forces because, again, we're dealing with a hydrostatic situation, and you need relative movement to have those viscous forces or tangential forces. Let's go ahead and look at the forces on the top and bottom. So on the top, let's start on the top. So the pressure force acting on the top will be pointing downward because it's normal and inward on the surface. Pressure there will be P, pressure we start with, plus here it's dp dy. It's how the pressure changes as I move in the y direction, times how far I've moved in the y direction, which is minus 1/2 dy. Why minus 1/2 dy? Because we're moving upward in the minus y direction. Remember, y is pointing downward here, so it's in the minus y direction, and we've moved minus 1/2 dy. Now the area for that face is going to be dx times dz. We can do the same on the bottom there. The pressure force will be acting upward. It'll be P plus dp dy times a positive 1/2 dy times the area dx dz. So those are the surface forces acting in the y direction. We can do the same thing in the z direction. I won't show it here just because it gets a little messy, but pause the video, try it on your own, and then you'll be able to check in just a moment whether you got it right or wrong. So now we've done all the surface forces. There's one other force we have to consider, and that's the body force, namely the weight. So weight is an example. Body forces are forces that act on all of the elements in the cube. So every little bit of mass inside the cube has a force acting on it. That's called a body force. And in this case, it's just weight that we're considering. So let me draw the weight. It's going to act in the same direction as gravity. Remember, gravity's shown up here. And the value for the weight will be the density times the volume. The volume is dx dy dz times the gravitational acceleration g. So those are our surface forces and body forces. Now let's go ahead and sum forces and set it equal to 0. We're setting it equal to 0 because we have a static situation. So we'll write that out here. So sum of the forces, we'll leave it as a vector. It's equal to 0. First of all, we'll write in our weight. Okay, so we have that term. Now let's put in the x forces. We'll write those in blue. So we have the x force on the left face. And that's acting in the positive x direction, so that'll be in the I hat direction. Remember, this is a vector. Then we have the pressure force acting on the right face. And that force is acting in the minus x direction, so that's why I have the minus here, minus I hat. Then we have the y direction and the z direction, so let's put those in. So let's start with the y direction. We'll have the pressure force acting on the top face, pointing downward. So that's in the positive y direction. And then we have one on the bottom face pointing upward, which is in the negative y direction. Oh, you know what? I realized I made a mistake when I wrote. Let me fix this in just a moment here. Up here in the x1, this term should be a positive 1/2 dx. Right here should be positive. I apologize, I put a negative there by mistake. So that should be positive. All right, so now let's do the z direction. This is the one that I wanted you to try on your own and see if you got it correct. So with pressure we start with, plus how the pressure varies as we move in the z direction. Right now I'll do the pressure force on the front face. So it'll be this face right here on the front, and it's going to be pointing in the positive z direction. So that'll be a minus 1/2 dz. And the area there will be dx times dy. It's in the positive k hat direction. Then the pressure force on the back face. I see another mistake I made in just a moment. I'll fix that. Okay, so there's the pressure force on the back face pointing in the minus z direction. So the minus k hat direction. The other mistake I made, I noticed I just put a minus sign there. That should be a plus sign. Let me fix that. So that's supposed to be a plus. Okay, so hopefully I didn't make any other little errors. So those are all of our surface forces. Now, we're going to simplify this, and you can see right away that there are certain terms that simplify. For example, the pressure term, this P will cancel out with that P because it's going to be P times dy dz minus P times dy dz, all in the I hat direction. So those will go away. Same sort of thing with these other pressures. So those will all cancel out. And then some other terms will add together. You'll see, for example, this term, the dp dx times a minus 1/2 dx times dy dz in the I hat direction will combine together with this one. There's a minus there, dp dx, 1/2 dx, dy dz. So those will actually combine together, and that's true for the terms in the j hat direction and the k hat direction. So all of those will combine together. Then the last thing that we'll be able to do is simplify by getting rid of the dx dy dz. You'll see here that this dx dy dz shows up everywhere. Right? There's a dx dy dz in all of these terms, so we'll divide through by that because in general that's not 0. So that simplifies things a bit. So let's write down what we now have. So we have 0 is equal to rho times g. That's a specific weight just written in a vector form. Then we'll have minus dp dx in the I hat direction minus dp dy. I'm not going to use the colors anymore. It's a little inconvenient to continue with. So that's what we have now, that we've eliminated a bunch of terms. And then we can write it one last, well actually the second to the last way that we'll write it. So we'll just bring the dp dx term and dp dy term and the dp dz term to the one side. And then the specific weight term to the other side. So that equation is the hydrostatic pressure distribution in Cartesian coordinates. All right, well, we can write that a little more compactly if we use the gradient operator, which is just del P is equal to rho G. It's the same equation. Just remember from calculus that the gradient operator is like d dx I hat plus d dy j hat plus d dz k hat. All right, so that's the gradient operator. So that's the hydrostatic pressure distribution. That equation is valid whether or not the fluid is incompressible or compressible. It doesn't matter what the density is. It's valid for any hydrostatic fluid. Okay. Now, this is a more mathematical way to derive it. I'm just going to show you a different way to derive it that's maybe a little more physical and give you a little better understanding. Let's go ahead and do that. So that will be it with this picture. Here, what I've done is I've got my large body of fluid, but now I have y oriented downward in the same direction as gravity. So gravity is in the positive y direction. In addition, I have the surface of my fluid here, right here. We're going to say this is like a liquid. Okay, so the surface here is what we call a free surface. And we signify that with a little upside down triangle. Sometimes they'll put little lines underneath it. So a free surface is just the interface between, let's say, like a body of water in the atmosphere. Right? It's like the surface of the ocean. So we can just call it a free surface. Up here, for example, the pressure might just be atmospheric pressure. Okay? So what I'm going to do in this derivation is I'm going to take a little column of fluid that starts at the free surface and goes down some depth y. And I'm going to make this cross-sectional area, let's just call it A. Okay? And I'm going to balance forces on that little column of fluid. So on the top, we have atmospheric pressure pushing down. So the atmospheric pressure force will be P atmosphere times A. We also have a pressure force at the bottom pushing up. We'll just call that P times A. And then we also have the weight of that column of fluid, which will be the density times the volume, which is just Y times A, times gravity acting downward. So there are no tangential forces on the surfaces because, again, it's a hydrostatic situation. Now let's go ahead and sum forces in the vertical direction. Set it equal to 0. So pointing downward, we have P atmosphere times A plus the weight, rho, y, A times G, and then holding it up is P times A. You'll see there's an A in each one of these, and then we can just rearrange it to get the following. That is our hydrostatic pressure distribution for this particular case. The way we can interpret this is it's really just a force balance, right? So the pressure on the bottom is required to hold up the forces above it. So imagine this pen is that column, right? Now I have to apply some force on the bottom. The force on the bottom is going to equal the force that I'm pushing down from the top, that's the atmospheric pressure times the area, plus the weight of the pen. So the force on the bottom has to support everything sitting above it. This is why, like if you've ever gone swimming in a swimming pool or the ocean or something like that, when you dive down deep into the water, you feel the pressure increasing inside your ears, right, on your eardrums. And the reason for that is because the pressure is increasing because it has to support the weight of all the fluid sitting above it. So that's why pressure increases the deeper you go. And you can see that here in this equation. The pressure at some depth y is the pressure you start with right up at the top, plus rho g, that's the specific weight of the fluid, times y. This is really just the weight of the fluid that you're supporting. So it's the pressure at the bottom has to support the pressure at the top, plus what we call a hydrostatic pressure contribution because of the weight of the fluid. Now we could have gotten the same equation using our previous derivation right up here. Let me just recopy this equation down here and we'll just rederive it. So remember we have this. Well, here gravity is just pointing in the y direction. So it'll just be rho times g in the j hat direction. It's in the positive. There's gravity. Here's our positive y direction. So when I write this out, I'll get dp dx is equal to 0. I'll also get dp dz is equal to 0. Let me just talk about those for a moment first. What that means is that there's no pressure variation in the x or z direction. So there's no pressure variation laterally. The only direction the pressure changes in is in the direction of gravity. Right? So you can go side to side in the fluid and the pressure will remain the same. That's actually very important and something that we'll use later in the course. So just keep that in mind. The only pressure variation you'll get will be in the direction of gravity. So now let me write what we have in the y direction. So that's what we have in the y direction. Turns out I can actually rewrite that in terms of an ordinary derivative. This is just a little math thing. In general, the pressure can be a function of x, y, and z, but from dp dx equal to 0, it means that there's no pressure variation in the x direction, so that means it's not a function of x. Similarly, dp dz equals 0 means there's no pressure variation in the z direction, so that goes away. And what I'm left with then is the pressure is only a function of y, So instead of using a partial derivative, I can use an ordinary derivative. It's just a little math thing. Don't worry about it too much. It just makes you have to be a little careful when you deal with mathematical notation. So it just makes it a little easier to solve the differential equation. All right, so now we have dp dy is equal to the specific weight. That means that the pressure, the change in pressure in the y direction is equal to the specific weight. It's just the pressure has to go up to support that little bit of weight. To solve that, I'll just bring the dy to one side and the pressure to the other side, and I'm going to integrate both sides. As y goes from 0, there the pressure is atmospheric pressure, to some arbitrary y, where the pressure is just some arbitrary pressure. Now the left-hand side of that will just be P minus P atmosphere. The right-hand side, in order to integrate that, I need to know how the density and gravity vary with respect to y. Now in general, gravity does vary with elevation, right? If you get far away from the center of the Earth, gravity goes down, right? The gravitational acceleration gets smaller. But you have to go really far away for that to make a difference, right? So for most engineering situations, assuming that the gravitational acceleration is a constant is a very good assumption. So we're going to make that assumption here. The other assumption we're going to make for this particular derivation is that the density remains constant, that we're dealing with an incompressible fluid so that we don't have to worry about variations in density. And that would be a very good approximation for liquids, like if we're trying to get the pressure at the bottom of the ocean, for example. Water is essentially incompressible. Now for gases, it's a little more questionable. If you're dealing with large elevation differences, then the changes in density for the air in the atmosphere could actually be significant. And we're going to deal with that just in a separate part at the end of this lecture. So for now, let me just assume that the density is a constant, that we're dealing with an incompressible substance. So we can pull the density and gravity outside the integral. So here I'm assuming rho is a constant and g is a constant. They don't have to be, but for this particular example, I am assuming that. And in that case, then the right-hand side just becomes rho g times y, which is precisely the same expression that I have up here. So what I've done is I've derived the hydrostatic pressure distribution for an incompressible substance here. And you can see from the example on kind of in the top there that what the hydrostatic pressure distribution really is a statement of is just a force balance, just supporting all the weight of the fluid and the pressure sitting above the point that you're interested in. All right, if I was to sketch what that pressure profile looks like, let me go ahead and do that over here. This would be the depth from the free surface, and this is the pressure. If I sketch out the gauge pressure, remember this P minus P atmosphere is just the gauge pressure, right? So if I sketch out the gauge pressure, it'll look like a straight line with a slope of rho g. So you can see how the pressure increases the deeper you go. If I was to do it in terms of absolute pressure, it would still be a straight line with a slope of rho g. It's just offset by the atmospheric pressure. So it's the same result. It's just whether you're dealing with gauge pressure or absolute pressure. All right. So that's the hydrostatic pressure distribution for an incompressible substance. So when we were talking at the very beginning about the basement wall and the water accumulating behind it, if the water gets deeper and deeper, you get larger and larger pressures and then larger forces acting on your basement wall. So that's why it's very important to get that water away from the wall so you don't get an increase in the pressure. All right, so now let's talk about what happens when you deal with a compressible fluid, like maybe the air in the atmosphere. Now in that case, I'm going to change my orientation. Let me use a different color here. I'm going to change the orientation of my axis since I'm dealing with the atmosphere. I'm going to put y pointing upward, like you're standing on the ground looking upward, and gravity pointing downward. I can still use my hydrostatic pressure relation. That looks like this, except in this case, gravity is pointing in the minus j hat direction. Right? It's pointing in the direction opposite to the y direction. So here again, I'll end up getting dp dy is equal to minus rho g So if I just, there's no variation in the x direction, no variation in the z direction, it's only in the y direction. Again, I can solve this differential equation. Actually, before I do that, let me just say one thing. Because I'm dealing with air in this particular case, I'm going to treat the air as an ideal gas. And so since it's an ideal gas, I know that the pressure and the density are related through the ideal gas law. So let me write that down. So from the ideal gas law, we know that the density is the pressure over gas constant and the absolute temperature. So I can substitute that in. It looks like that. I can bring all the p terms to the left-hand side and the y terms to the other side. So there's our differential equation now. Let me go ahead and integrate both sides. So we're going to go from P, I'll just put some initial pressure P naught to some final pressure. And the right side will be going from some initial position to some final position. Now the left-hand side of that will be a natural log, P over P naught. The right-hand side, well, gravity, we already said we're going to treat that as being a constant. R is the gas constant for air, so that's just a constant. So those will come outside the integral. The t, however, I'm going to keep inside the integral, and I'll talk about that in a moment. So we have a g over r integral of dy over t. Now, the temperature does in fact vary with altitude, and you probably have some experience with this. If you've ever gone into the mountains, you know that the higher you go in elevation, the colder it gets, right? Or if you've gone flying in a commercial jet, a lot of times they now have little LCD panels in front of the seat that'll tell you how fast you're going, what your altitude is, where you're located, but they also will tell you the temperature, and you'll notice that the temperature outside is often really cold when you're up at altitude. It's very, very cold. So the higher you go in altitude, the temperature actually goes down, and people have recognized this for some time. And in fact, they've made many measurements of how the temperature varies with altitude and combined those measurements into a standard called the US standard atmosphere. So we know how the temperature varies with altitude from all these measurements. So if you look at the screen here, you'll see a picture of that just illustrated. So the atmosphere is actually divided into certain parts. Where we live is down here in the troposphere. That's near sea level. And then the troposphere goes up to about 10 kilometers. So right toward the top of Mount Everest. Mount Everest is at about 9 kilometers in altitude. Commercial jets fly right at the edge of the troposphere. Once you get above the troposphere, you're into the stratosphere. So commercial jets are right at the edge of that. In the stratosphere, you can see here spy planes are flying at about 20 kilometers. I think like the SR-71 and the U-2 are air-breathing spy aircraft. They're about the highest altitude aircraft that we know of, at least. They're close to 20 kilometers, something of that order. 90,000 feet, I think, is roughly the height. And then stratosphere is kind of a large part of the atmosphere. Weather balloons they're at about 40 kilometers. One interesting thing about weather balloons is Felix Baumgartner, who set the world record for the highest skydive. He was in a weather balloon that went to, I think, 39 kilometers and then jumped out and did his world record-breaking skydive. When he jumped out, the atmosphere was so thin where he jumped out, he actually broke the sound barrier, went very fast. Air drag was very small because there wasn't much air around him. So he broke the sound barrier, and he also had a tough time controlling his position in the air. Normally you put your arms and legs out to try to give you some control surfaces to control your position, but because there was so little air, he couldn't really do that, and he started to spin, and there was concern that he would black out from that. But fortunately, he got it under control and landed safely. So there's actually a nice documentary about his skydiving events, so you might want to take a look at that. It's pretty cool. So we have the troposphere, the stratosphere, the mesosphere is above that. That's where you're getting into rock. It's very upper edge of the atmosphere, and then the thermosphere is right on the edge of space. Okay. Now, if you look on the right-hand side of this, you'll see the temperature as a function of altitude, and you can see it starts at about 15 degrees C, and just decreases linearly as you go up in altitude. And then it kind of holds steady and then increases and decreases again. Each part of this curve here is actually piecewise linear. What it means is that they're just line segments all connected together. So we could describe the temperature at any altitude as just T is some linear function, T naught minus beta y. Right? It's just the equation of a line where the T naught and the beta vary depending on which part of the atmosphere you're in. So we could take that T, put it into our equation here, and then integrate it. And if you do that integral, it'll look like another natural log term. Okay? I'm not gonna show the rest of the derivation for that. I'll just give you the final result. So specifically, what we'll get is natural log of, well, let me just give you the final result. I won't go through all the math of it. We'll get P over P naught is equal to 1 minus beta y over T naught, all raised to the G over beta R. So that's the result that you'll ultimately get. And this specifically is for the troposphere. That's the part that we're most interested in because we're dealing with things close to sea level in most of our engineering applications. So in the troposphere, the Y naught was 0 because it's going from sea level. The T naught is 288 Kelvin or 15 degrees C. So that's our standard atmosphere. The P naught will be 101.3 kilopascals absolute, again corresponding to standard temperature and pressure. And then the beta is 6.50 Kelvin per kilometer. So the temperature drops 6.5 degrees Celsius or 6.5 Kelvin for every kilometer you go up in altitude. So to kind of give you some English units to go along with this, the 288 Kelvin is about 59 degrees Fahrenheit, and the beta is about 40, that should be an approximate sign. It's about 4 degrees Fahrenheit for every 1,000 feet. It's kind of a handy number to know. If you ever go hiking in the mountains, every 1,000 feet you go up in altitude, the temperature drops roughly 4 degrees Fahrenheit. Okay. So now that we have that relation, so this is how the pressure varies in the troposphere as you go up or down in altitude. What I want to do is, let's see how far we have to go up in altitude to drop the pressure by 1%. So to do that, I want to know when the pressure is 0.99 compared to the sea level pressure. So it's just a change in 1%. If I plug in the numbers for this and solve for y, I'll get that y is 85 meters, or in English units, that's about 280 feet. So to get a 1% change in the pressure in the atmosphere, I have to go up 85 meters, or roughly a 28-story building. That's a pretty big distance to make such a small change in the air pressure. So what we can conclude from this is that when you're dealing with gases, like in the atmosphere, we don't really have to worry much about the changes in pressure as we change elevation. In a liquid, you certainly have to worry about the pressure changes as you move up and down in the liquid, because liquids are very dense, right? They're 1,000 times more dense than gases. So if you even have a 10 centimeter change elevation in a liquid, that's a significant, you have to account for that kind of pressure change. But if you're dealing with a gas, you have to go, hundreds of meters before you get any appreciable pressure change. And that's because the density of gas is just so low, you have to pile so much gas on top of it for it to have any noticeable effect. So when we're dealing with gases, under ordinary engineering conditions, don't worry about the pressure changes due to elevation. They're just not that significant. Okay? They're there, they're just not that significant for most of our purposes. All right, I think I've covered everything I want to on this topic, so just make sure you review the notes and do the corresponding reading, and I'll have some examples that are related to this topic in separate videos.